Thanks a lot, Mariam. Thank you very much for the invitation. It's my first time here. It's a great pleasure. First, I will more or less apologize because I had told Mariam first that I would talk about cosmology, but because this week there are a lot of early rumors this week that today there's going to be a big announcement. We're probably going to learn about gravity waves, whether they exist or not today, this afternoon. So I thought I was not talk about cosmology, but talk about my other area of research, which is black holes and gravitational waves as well. So I want to tell you about the work that I have been doing for the past year. Part of it was already published as a letter earlier in 2015, but most of the things I'm going to talk about are also work in progress. So it's about superradiant scattering of gravitational waves mainly from astrophysical black holes in binary systems. So the main goal of this work is to try and test this phenomenon of black hole superradiance. I'm not sure if anyone has ever heard about this phenomenon. It's a very interesting thing. If you have a rotating black hole, here depicted in this cartoon, with a certain rotational velocity, omega, at the horizon, if you send a wave into the black hole, the wave will be scattered, just like in any problem. Part of it will be absorbed, part of it will be reflected. But rotating black holes has this very peculiar property that they can amplify certain waves, in particular certain wave modes. If the wave has sufficiently low frequency, below a multiple of the angular velocity of the horizon, and I'll explain what this multiple is, then you can have reflection coefficients larger than 1, meaning you have the reflected wave is larger than the incoming wave. And this is because there is extraction of energy from the black hole. The black hole will lose mass and will lose spin. It's essentially the rotational energy that the wave is stealing from the black hole in this rotation, in the scattering process. And for electromagnetic waves, you can get amplification factors of order a few percent, not very large. But for gravity waves, the amplification factors can go above 138%. And this is a result that has been known since the seminal work of Tucholsky and Kress back in the 70s, starting with Zeldovich. But it's been a theoretical phenomenon ever since. So what I wanted to know is whether we can observe this phenomenon in astrophysical systems, whether something like this can occur. So the plan of my talk to explain how this phenomenon occurs first, what is black hole superradiance, and then to tell you about how I plan to see whether this can be observed. I'm going to tell you first about how to decompose plane gravitational waves in different modes, to see which of these modes are amplified and which are not amplified. And then I'm going to tell you about a few examples in the observational prospects and challenges of how this can occur in astrophysical systems. So first, here's the metric that represents the space-time known as the Kerr space-time. Represents a rotating black hole, written in the so-called Boyer-Lindquist coordinates. These are just the essentially spherical coordinates, if you want, analogous to the Schwarzschild case. The difference is that the black hole has a mass m, and it has a spin parameter a, which can be between 0, that's the non-rotating case, the Schwarzschild black hole, and capital M, which is the extremal rotating case. Why there is an upper limit? Because the horizon of the black hole is at this coordinate. And you can see that if A becomes larger than M, then you get an imaginary value for the horizon, means you get a naked singularity. So assuming that this does not happen in nature, that's the cosmic censorship conjecture, this has an upper bound on the spin parameter. And there's also in this space-time a region called the Nergal region, bound by a Nergal surface with this expression, which surrounds the black hole horizon. And it's a region where the killing vector associated with time translation, so the DDT, it becomes space-like. And this means that an observer far away from the black hole, if he tries to measure energies of particles or waves inside this region, he can measure negative energies. There can be negative energies from a point of view of an asymptotic observer going into the black hole. It means that there is energy extraction. This is the basis of the so-called Penrose process, and it's also the basis behind this phenomenon of superradiance. It becomes extremal when the spin parameter is equal to m. So A equals 0 is Schwarzschild, A equals m is the extremal limit. It's the maximum spin. This is the spin parameter. I'll show you in a minute what's the actual expression for the spin. Okay. So The angular velocity depends on the distance from the horizon, but at the horizon is given by this expression. And for what I want to do, it's very useful to have some numbers in mind. So this is the actual spin. It's the spin parameter times the mass times the velocity of light. We can construct a dimensionless quantity, a tilde that goes between 0 and 1, 0 being Schwarzschild, 1 the extreme limit. And the angular velocity of the horizon is, for a black hole of about 10 solar masses, is around 10 kilohertz. And if you go to very much larger black holes, this angular velocity decreases. So keep this number in mind, around kilohertz, because this is going to be relevant for what I want to talk about. How do we go about solving a scattering problem in the Kerr spacetime? We want basically to solve the equations for wave propagation in the spacetime. They can be the Maxwell equations, if you want to talk about electromagnetic waves, or the perturbed, the linearized Einstein equations, if you want to talk about the propagation of gravity waves. And this has been it's a difficult problem because these equations are many equations, they're coupled together, sometimes they can't even be solved in an easy way. But back in the 70s, people developed a very interesting formalism that helps us to solve scattering problems in this spacetime and other related spacetimes. And this is the so-called Newman-Penrose formalism. What you do is you take a tetrad, so a set of 4 vectors. In this case, it's a null tetrad, so all these 4 vectors are null. They have 0 and 1. This is the kinetic tetrad, which is particularly appropriate for the Kerr spacetime. Never mind the exact expressions. But what you do is you take, for example, the electromagnetic, the Maxwell tensor F mu nu, and you project F mu nu along these 4 vectors. So you can construct scalar quantities. So for example, you have the scalar quantity phi naught, which is this particular projection along L and M. And along M star and N, you have phi 2. Okay? For the gravitational waves, you can take the Weyl tensor of your spacetime, so the part of the Riemann. Yes, sorry. Sorry, actually the notation, it's M bar actually. So these are complex. So it's actually a good point. So even though the Maxwell tensor and the Weyl tensor here for the case of gravitational waves are real, these are complex vectors. So these scalars will be complex scalars, which is an important thing. So for the case of gravitational waves, you project the Weyl tensor, which is the part of the Riemann tensor that is not connected directly to the energy momentum tensor. And this is very useful to study the gravitational wave part, the radiation part of your problem. What you do is you get these scalar quantities, and you can show that actually if you see what these quantities correspond to, you're going to see that at infinity they correspond to these correspond to incoming and these to outgoing radiation. And more importantly, they basically separate the different spin components. So you know, for a Maxwell wave, you have spin plus and minus 1. These are minus 1 and plus 1 components. For a gravitational wave, you have spin plus and minus 2. These scalars represent the spin minus 2 and plus 2 components. Okay? The usefulness of this is that you can turn all these coupled equations into scalar wave equations. They all decouple. Each of those scalars satisfies a decoupled equation from the other. So you turn a complicated problem into something that you can solve. And more than that, you get wave equations that you can solve by separation of variables. So I'm not going to show you all the details, but this is the point. So anything that you can solve by separation of variables becomes an easy problem, or somewhat easier. So for example, this represents all those scalars with different spin components. You can separate the time and the angular dependencies and the radial dependence in the spacetime into all these different functions. And you plug this into the equations, and you get, the frequency dependence is just e to the minus I omega t. The azimuthal angle dependence is e to the I m phi, and this is the m parameter that I showed you before. It's the integer. So you have angular momentum modes for the waves, L and M. You have a radial wave, for each spin S, and you have a frequency over it. And you can see that the equation for the angular part, so the theta and phi part, if you go into the limit of Schwarzschild, it satisfies the so-called spin-weighted spherical harmonics equation. So these are similar to the usual spherical harmonics, but they are spin for arbitrary spin. If you go to non-zero spin, so the Kerr spacetime, you have corrections, so they become spheroidal harmonics. It's a known equation, and the eigenvalues of this equation are L plus 1. This is the case of spherical harmonics. minus s plus 1, this is the spin-weighted part, plus corrections, which come in powers of a omega. If this is small, we can, in principle, neglect or just include a few terms in the series. This is the angular part. So you basically reduce the problem. These dependencies is trivial. You reduce the problem to solving a radial equation, a one-dimensional equation, which is what you want to have in a scattering problem, essentially. This is known as the Tucholsky equation, because Tucholsky was the first to derive this equation and work it out also with Bill Press back in the 70s. It has a complicated form. I don't want you to understand all these things that are here. I want you to understand the main things. One thing is what you can do with wave equations that look complicated is you can rescale your radial function by some other functions. Yes? Yes, either the perturbed Einstein equations or the Maxwell equations. This is an equation that you can use actually for even the Klein-Gordon equation, which is spin 0, reduces to this generic equation. So you just have to put spin 1 for Maxwell fields, spin 2 plus minus 2 for the linearized gravitational perturbations, or spin 0 for Klein-Gordon actually. Okay? And these reduce to a master equation, master radial equation, which you can solve for general S. That's the idea. But it's a single wave, one-dimensional wave equation. This is particular to the Kerr spacetime. It doesn't happen in all spacetimes, and you have to make that particular choice of the tetrage, the way you construct those scalar functions, okay, out of the relevant texts. Okay. These are perturbations. It doesn't mean that. So the Kerr spacetime does not have an electric field, right? So there's no background electric field, but you can have waves propagating in that geometry. So these are test fields. So you solve the Maxwell equations as a perturbation in the Kerr spacetime. The same way you solve the linearized Einstein equations on top of the background of the Kerr spacetime. Okay, so these are perturbations. These are like just waves that you are propagating in this background. Fixed background space. Okay. It's the test field. So you get a one-dimensional equation. Now, as I was saying, you can recast it into a more familiar form. If you change into the so-called tortuous coordinates R star, so it's a rescaling of the radial coordinates that puts the horizon at minus infinity, plus infinity. It used to be plus infinity, but it kind of stretches the problem to minus infinity to plus infinity. And you also rescale the radial function, call it psi, you get an equation which has a Schrödinger form. Okay? And this Schrödinger, but with the omega squared instead of an energy. But it's essentially the same type of equation. And we know how to solve these things from quantum mechanics. We just have to look at the shape of the potential. The potential is something that you extract by doing this procedure, and it has this typical form. It goes to 0 and infinity. It has an angular momentum barrier, just the usual L plus 1, but for non-zero spin. And close, as soon as you go into that ergo region and to the event horizon at infinity, this potential becomes a constant. Okay? So you can do this, I like to explain this in terms of this toy model, where you basically, instead of having a barrier, you put there a delta function, you just put constants here to the left and to the right of the barrier. And you can read this constant actually from the Tucholsky equation. So, yes? Now, omega is the frequency of the wave. Omega comes from the mode decomposition. Okay? It's a property of the wave that you're going to send to the space thing. Okay? R is a radial coordinate. So this is just a scattering problem. You're going to send a wave of a given frequency, and you want to see what comes out. So this is the basic idea. That's why I'm reducing this to this one-dimensional problem. Well, you can reduce it to a one-dimensional problem. It has a potential with a complicated shape. But just to illustrate, let me replace this barrier by a delta function with an arbitrary height. It doesn't matter. I just put the constants that I get from the Tucholsky equations, this, on the left-hand side of the barrier, so close to the black hole horizon, and the potential, I just put it 0 in the second region. So the scattering problem, this is something you can give to quantum mechanics students, actually. So it's an interesting problem. You have an ingoing wave, you have an outgoing wave. On the left-hand side, you just have a wave ingoing into the black hole, because there's nothing coming out of the black hole. Okay? So you just solve that Schrödinger equation, Schrödinger-like equation, in regions 1 and 2. You just have plane waves in both regions. But the phase velocity of this wave is different. It has a combination omega minus m, the azimuthal angular momentum number times omega. And here you have the two waves. But then you do the familiar thing. You impose the continuity of the wave function. There's a jump in the wave function because of the delta barrier function. And you can solve for these coefficients, and in particular get a reflection coefficient. So what's the ratio between the amplitude square of the reflected wave and the ingoing wave? Okay? You get this expression, and you can see that this expression can become larger than 1 when omega is less than m capital omega. Okay? This is the point where you get reflection coefficients larger than 1. It's exactly that condition that I mentioned in the beginning. Okay? And this, of course, this is a test field approximation. The true thing you have to do with numerics to show that this is actually extracting energy from the space-time. So this back reacts. This extra energy used to amplify the wave comes from the rotational energy, essentially, of the black hole itself. But this is an interesting toy model that you can use to show that you have a superradiant scattering, this amplification of some particular wavelength. We can do a bit better than just solving toy models. We can actually take the Tucholsky equation. You can't solve it exactly completely, but you can do a trick, which is to separate two regions. One which is closer to the horizon than the wavelength of the radiation, essentially, where you can solve exactly in terms of a hypergeometric function. This is a rescaled coordinate. You can solve it exactly far away from the black hole horizon, where you get a combination of confluent and hypergeometric functions. And what you can do is, if the wavelength is sufficiently large, these regions will overlap. So these solutions should be both valid in an overlap region. So you can match them together to get the coefficients that you're missing here, there. Okay? When you do this matching procedure, you can actually compute what is the energy at infinity of the incoming wave, of the outgoing wave compared to the incoming wave. So the fluxes, you actually can check what is from the energy momentum tensor of the Maxwell field, and for the pseudo energy momentum tensor for the gravitational waves, that the incoming and outgoing waves are given in terms of phi naught, phi 2, psi naught, and psi 4, the scalars that I mentioned in the beginning. Okay? And computing this, you actually get an expression, not for the reflection coefficient. This is something that was introduced by Tucholsky, is the gain loss factor, the Z, which depends on the particular wave mode L and M, which is the ratio between the outgoing energy, flux, over the incoming flux, minus 1. And by conservation of energy, this is related to the energy that goes into the black hole. So if you have superradiance, the outgoing flux will be larger than the incoming flux, and this is going to be positive. Okay? And the energy going into the black hole is negative. It's related to that negative energy that I told you was possible in the Kerr space. So this is just the result of the matching procedure. You get a complicated expression, but you see it's proportional to the combination omega minus m omega. This bar just means it's measured in units of the horizon. Okay? But you can see that if omega is less than m omega, this is negative, and this is positive, means you have more outgoing energy than incoming energy. You have the phenomenon of superradiance. Okay? This is only possible for very small frequencies, when you have an overlap between these two regions. But we can do better if we're going to study the full process. You have to do numerics. What you can do, just in a nutshell, is to start with the solution very close to the horizon. It has this particular form in terms of a rescaled variable. Yeah. Well, sorry, I've hidden it in terms of these variables. This is it's here in this tau. Okay. Tau equals 0, it's the extreme things. Tau equals 1 is the short things. It's just the reason. You just have to rescale the variables to make it look nicer. Okay. But you can see it's there in the angular velocity. This is the basic important part of this proportionality. So to do better, you have to the solution very close to the horizon, and you expand in powers of x, where x is the rescale distance from the horizon. Okay? And you can do this you can just find these coefficients with Mathematica, analytically. And then you use this as a boundary condition close to the horizon, and you integrate up to infinity, where you can measure the amplitude of the incoming and the outgoing wave when you take the ratio to get the z factors, essentially. Okay? It's not, the rest is just algebra and implementing numerical calculus. I just want to show you the results. This is something I've done, but trying to basically reproduce the results that Professor Tucholsky got back in the 70s. So here's an example of gravitational waves. A black hole very close to extremality. So this is not exactly 1, but very close. Numerically, it's very difficult to get to 1. And I'm just plotting the modulus. Okay, so this is always positive, so I can have a log plot. So these are the 5 modes with L equals 2, the quadruple. So what happens is that the m equals 0, m equals minus 1, and m equals minus 2, z is always negative. Means that you always have less outgoing energy than incoming energy. You don't have superradiance. For these modes, you don't see this. For the m equals plus 1 mode, it's positive here, where the superradiant condition, where omega is less than capital omega, than the angular velocity of the horizon. You see that this is positive, then it has a 0, then it becomes negative after for larger frequencies. For the m equals plus 2 mode, as long as omega is less than twice capital omega, so instead of 0.5 in these units goes to 1, this is always positive. Okay? So these modes can be superradiant, the positive m modes, but these are always non-superradiant. It means that the waves are never amplified. Okay? But this is only true when I define omega to be positive. What does this mean? Let me just go back to I did an expansion, which was e to the minus I omega t. In general, I'm gonna, because the actual waves are real functions, the metric is real, the Maxwell tensor is real. I'm also gonna have combinations which have e to the I omega t. So I define them in terms of this being positive frequency, but there being a negative frequency as well, which corresponds to the other combination. In that case, what happens is that I get essentially the same result, but when I change omega to minus omega, I change m to minus m. So for the positive frequencies, these are the superradiant modes. For the negative frequencies, these are the superradiant modes. Okay? And let me just summarize. The Z factor, for positive frequencies, you're going to have amplification if omega is positive in that definition, and m is also positive. Or if omega is negative and m is negative. And numerically, you see that the Z factors go from -1, where the waves are completely absorbed by the black hole, nothing comes out. Okay, this is what happens in the high frequency levels. Or in the superradiant regime, they can be amplified up to 1.38. This is very close to extremality. I actually only got to as far as 1 numerically. But you can get waves that are completely absorbed. You can have waves that more than double their amplitude with the by scattering of the central black hole. Okay? So now my idea was to see, I want to see if this is possible in astrophysical systems. And in astrophysical systems, you can imagine that you have some source of radiation, either electromagnetic or gravitational, and you want to see what happens to that overall wave. Okay? And that wave will in general have different m modes, different L and m modes, and different positive and negative frequency modes. So we have to see which of these modes are superradiant and which of these modes are non-superradiant. Some of them will be amplified, some of them will be absorbed. So you have to see what the overall effects are. So my goal as a first approximation was to say, if I have a source sufficiently far from the black hole, the waves produced by the source are essentially plane waves. So I'm going to study what happens to plane waves that I send from infinity into the central black hole, see what comes out when I sum over all the modes that wave has. Okay? And I want to see if the superradiant modes can be the dominant in the incoming wave, such that overall the wave is amplified. I hope this is clear. This is the goal. I want to see if the superradiant modes, the ones that are amplified, win over the non-superradiant modes in a generic plane. Okay? So what I did was to take a plane gravitational wave in the TT gauge, where you can write in this particular form. You have an e to the minus I omega t plus IKR, the standard plane wave factor. And then you have the two polarizations, H plus and H cross of the gravitational wave. And these are the polarization tensors when you have an arbitrary direction in the angles in the Kerr geometry. So and theta naught and phi naught, this is the direction of the wave. These are the polarization. And you're going to have the complex conjugate of this because overall this has to be real. So we have an e to the minus I omega t, and you're going to have an e to the I omega t. So a positive frequency and a negative frequency. What I want is what is the general decomposition of this in terms of Lm modes, okay, in terms of harmonics. So what I did was to compute that Newman-Penrose scalar, so that projection of the Weyl tensor. So I take that metric perturbation, I compute the Weyl tensor, and I project it into a particular tetrad, and I see what I get. And I take the large distances approximation. And what I see is the following. This scalar indeed has a decomposition of the form that I showed you before. It has an e to the minus I omega t. And it has different, it can be decomposed into different, here I call it Jm modes. So these are the spin-weighted spherical harmonics. This is far away from the black hole, so it's essentially flat space. Yeah, sorry. Well, to do this, what I want to see is what is my incoming wave at infinity to set the boundary condition for my scattering problem. So at infinity, I'm just using flat space. Okay, I'm just seeing what happens in flat space to a standard plane wave to see what is the mode decomposition to use this as the boundary condition, the incoming wave for my scattering problem. Okay, so I do this in flat space. Thank you, and I obtain spin minus 2 spherical harmonics. Okay, as a function of theta and phi. And the amplitude of each of these harmonics is modulated by an analogous harmonic in the direction of the wave. So the angles theta naught and phi naughts that I fix as the direction of my wave. I see that it has a part which is ingoing and a part which is outgoing. So if you think of a plane wave, some part is approaching the black hole, some part will be going away. I want to take the ingoing part as my boundary condition. Okay. And I see that there's an overall amplitude here, which is the combination of the two polarizations, H plus minus I, H cross. Okay? And I'm going to have an e to the minus I omega t, and I'm going to have the analogous part with e to the I omega t. And I see that when I change this, I get exactly the same result, but I change these, H plus and H cross, into their complex conjugates. So then I compute what is the ingoing energy for each Jm mode of this incoming wave. And I find these very simple expressions. Means that for each mode, the amplitude of each mode is modulated by a spherical harmonic corresponding to that mode, Jm, okay, with angle momentum Jm. And I have a different amplitude for the positive frequency part and for the negative frequency part. So the e to the minus I omega t and e to the I plus I omega t. Why is this important? Let me show you the spin weighted spherical harmonics. Okay, they're very similar to the spherical harmonics, but have some subtle differences. So the modulus does not depend on phi, it just depends on the theta naught, so the polar angle direction of the wave with respect to essentially the black hole spin, which is aligned with the z axis. So these are non-superradiants. For the negative frequencies, I find the opposite. That these will not be superradiants, and these will be superradiants. Okay? So there's an interesting game. Imagine that I choose my wave to be incident along theta naught equals 0. So the wave is only made of m plus 2 modes. Okay? And this is actually true for higher L. Then this part of the wave with positive frequency would be amplified because it satisfies the superradiant condition in the region where the frequency is small enough. But this part would not satisfy. So this part of the wave would be absorbed, this would be amplified, and this part would be absorbed, and overall the effects would cancel. If I want to have an overall amplification, I have to make these amplitudes, the intensity of the positive and negative frequency parts, different. So this is what I mean by the statement. If I want to have an overall amplification, this is one of the basic things that I need. I need a polarization of the wave. If these functions are real, H plus and H cross, then these two things will be equal. Then I'm never going to have an overall amplification. If, however, they are different, then I can select different M modes by selecting the direction of the wave, and I might be able to have the superradiant modes winning over the non-superradiant modes. Okay? So I'll show you this. So basically, the conclusion of this generic study is if I want to have an overall amplification of an incoming wave that goes from infinity, so from some source very far away from the black hole, I need the wave to have sufficiently low frequency to satisfy that superradiant condition. And going back to what I put in the beginning, if I have a black hole with 10 solar masses, I need frequencies below a kilohertz, essentially. 10 kilohertz, 1 kilohertz range. I need the wave to come from some particular direction or have some directional dependence, so I can select the dominant M modes to be different as the direction of the wave varies. And this is why I want to look at binary systems, where the direction of the wave, because the direction of the source is changing, the direction of the wave is going to be moving. And I need a non-zero polarization because of what I told you before. I need to separate those positive and negative frequency parts. And this is the non-trivial bit. Okay? So now I want to tell you about examples of where all these three conditions can be satisfied, and I can have an overall amplification of an incoming gravitational or electromagnetic wave, something that could eventually lead to observational prospects in the future. So, for any source, if I wanted to, I'm going to focus on the case of gravity waves, which is where the amplification factors are larger, as I said in the beginning. For any source, I can compute what is the gravitational radiation it emits by using the well-known quadruple formula. If I have the moment of the inertia tensor of the source, I can compute its quadruple moment, take the second derivative, and do this particular projection along the direction of the wave. This is the unit vector n along the direction of the wave. This is pretty standard. So this is the position of the wave, of the source at RP, and I evaluate the quadruple tensor at the retarded time. This is the standard thing that I'm assuming most of you will be familiar with. If you take just an oscillating quadruple, so the t dependency to the minus I omega t, for example, when I evaluate at retarded time and take the distance from the source to be very large, I can show that this just has the plane wave form up to a phase. This is why I said if I take the source to be sufficiently far away, I get a plane wave. But this is also a result which is familiar from electromagnetism. Okay? But it also happens for the case of gravity waves. So I just have to see, well, let me take some particular source, let me get the quadruple moment, let me get this H, Ij, and then let me compute those two polarizations, H plus and H cross, by projecting into those polarization tensors that I showed in the beginning. Okay? And then I can see whether I have the polarization. So the first source is a pulsar. A pulsar is a rotating neutron star. It's thought to be a remnant of a supernova explosion. It's made of neutrons. It's very compact, but not yet a black hole. It's the last stage of stellar collapse before it becomes a black hole. They have around 1.4, not much larger solar masses, 10 to 20 kilometers, and they are rotating with frequencies in the 1 Hz to 1 kilohertz region. They have enormous magnetic fields because when the star shrinks, conservation of flux implies the magnetic field at the surface becomes enormous. So as they rotate, they basically, yes? You mean for the purposes of the problem or in practice? Radio. This is radio for electromagnetic waves. Is this the question? Sorry. It's radio. It's radio waves. It's in a very low radio limit. Okay? I'll mention that in a minute. But they behave essentially, I don't know if you can see this figure, they're just basically like magnetic dipoles precessing around an axis. You know that this emits radiation, magnetic dipole radiation. This is one thing which you can use. The radiation has, as I was saying, radio frequency. It's in the right frequency range to be slow enough so that the black hole could amplify these waves. But for me, the most interesting thing, because as I said in the beginning, the amplification factors are much, much larger for gravity waves. Everything I've shown for gravity waves can be done for electromagnetic waves, actually. So it's a parallel for spin 1 and spin 2, we can do the same. But focusing on the gravity waves, these rotating neutron stars, they can also emit gravity waves. And the reason is that they have a non-vanishing quadrupole moment because they're not perfectly spherical. Okay? whenever there's a disturbance in that sphere, whatever small enough, you create a quadrupole. And you emit low-frequency gravitational waves, which have exactly the same frequency as the rotation velocity of the star. Again, in the 1 Hz, 1 kHz region. And this is in the range of gravity waves that advanced LIGO, which we're going to hear about today, is going to be sensitive to. And also advanced Virgo and other experiments which are upcoming. So how do you compute the gravitational waves from a rotating neutron star? Well, I kind of exaggerated in the figure here. If there's a mountain or if there's something that makes it not exactly spherical, it becomes, the first approximation, an ellipsoid that is rotating. I'm going to take the case where it's rotating about the z-axis, which is the axis of rotation of the black hole as well. So the spins of the neutron star and the black hole being either aligned or anti-aligned. But the principal axis of inertia, which I'm calling z hat, is misaligned by some angle which I'm calling beta. So you compute the moment of inertia and the corresponding quadrupole moment in the frame which is not rotating. It has this particular form, but this is the principal axis of inertia. This has to be traceless. That's why this form. And then you just rotate, perform a rotation on the tensor to get the quadrupole moment in the black hole space, the frame which is not rotating. And this is what you have to put in the quadrupole formula. And you find this very peculiar form. It has a pod which is oscillating with frequency omega p, but the spin-to nature of this makes it have also a pod that's rotating with frequency twice omega p, where omega p is the rotational frequency of the pulsar, of the neutron star. And these two parts, they depend on the inclination angle, the amplitude in each of them. And they have a tensor structure which has these two particular forms. And they're very simple. They're reminiscent of Pauli matrices, actually. And the upper and lower signs, which I included here, correspond to the cases where the rotation is aligned with the z-axis, so with the black hole rotation, or the case where it's anti-aligned. So this is just for simplifying. You can do the more general case, but it just becomes quite messy to show. So you get the quadrupole tensor, you put in the quadrupole formula, and you can get the two, you basically project in those plus and cross tensors to get the different polarizations. First, let me show you you can compute the overall power in these two components, what is emitted in gravity waves, for typical values. So a pulsar which has a period of a millisecond, so rotating with kilohertz frequency, this is called a millisecond pulsar, with typical values for the mass and the radius, with an ellipticity, so deviations from eccentricity defined like this, of just 10 to the minus 5, as a luminosity in gravity waves power, which is around 10 to the 9 times the solar luminosity. So it's huge, okay? They lose a lot of energy, rotational energy, via gravity waves. This have yet to be detected, okay? But this is one of the things that LIGO is looking for. So, but as I was saying, I want to see the polarization of this wave. So just here's a cartoon. I put the pulsar. It's rotating about the z-axis, just like the black hole. Set at some given position, given by the angles theta p and phi p, which is going to determine the direction of the waves that it emits. Okay? There's the angle beta between the principal axis of inertia and the rotational case. And at very large distances between the pulsar and the black hole, I'm just going to get a plane wave, as I explained before. But the polarizations, which are the important thing, I can compute the combinations H plus minus H cross, so the two polarizations of the gravity waves. For the single frequency, so the one that rotates with the same, the part that oscillates with the frequency of the rotation, I get this complicated expression where I see that this combination, which is the relevant one for superradiance, is proportional to spin-weighted spherical harmonic with L equals 2 and M equals minus or plus 1, evaluated at the position of the source. So where I put the pulsar, I'm going to get this polarization. And the one with a plus, so this is what's for the positive frequency part, for the negative frequency part, I got a similar result, but it's not the same harmonic. It changes the M. And as I showed you before, changing the M changes completely the angular dependence, as I showed you before. So the waves are actually polarized, and I interpret this as the fact that the source is a rotating source. It actually polarizes the waves that it emits, and it gives the polarization exactly that I need to have with superradiance. I can get the same result for that part which rotates with twice the frequency. I think it's a very mathematically very nice result that you also get a spin -2 spherical harmonic, but with m equals minus or plus 2, or plus or minus 2 in different cases. But again, I get the polarization, which depends on whether the pulsar is rotating in the same sense as the black hole or in the opposite direction. Minus and plus sign, plus and minus. Okay. So basically, I can get what is from the energy in gravity waves that the pulsar is emitting. I can take the incoming parts, and I get this very simple expression. P is the total power. This is actually valid for both gravitational and electromagnetic waves. I did the same analysis for both. And you get this a very simple expression in the end. This is the overall power. This is the energy in each LM mode. It depends, as I told you before, each mode, there's a dependence on the spin-weighted spherical harmonic L and M, which separates the different modes. This is what I've told you before. It was in the direction of the wave, which I called theta naught and phi naught before. This is just the inverse of the position of the pulsar, theta d, phi d. And then the combination for the positive and negative frequencies gives me another spherical harmonic. These are the things that I just show you in this combination, H plus minus I H cross. Okay, and there's and this, the incident energy falls with the square of the distance between the black hole, between the pulsar and the black hole. This is the usual, just falling with the square. So this allows me to know how much energy I have in each mode L and M as a function of where the pulsar is, the angular position and the radial distance, okay, so I'm calling LP. Now, what I do is I want to know what's the outgoing energy of the scattering process for each LM mode. And these all, I remind you that you can, because you solve the equations by separation of variables, it means that each of these modes satisfies a separate equation. So I can, the scattering problem, I can do it separately for the different modes. Each mode, I know what's the incoming energy, and I can use those techniques, analytical and numerical, that I showed in the beginning to get basically the reflection coefficients, the gain loss factor, to see how much energy is coming out of the scattering process. Okay. So here's a result. Okay. This is for a black hole, again, very near extremality, and a frequency very, very close to the upper limits of the superradiance condition, the m omega for m equals 2. This is where the amplification factors get close to 1, as I showed you before. So this is kind of a best case scenario, if you want. So what I see is, as a function of the angular position of the pulsar, which determines the direction of the wave, okay, I have the variation of basically the power in gravitational waves that comes out. I basically subtract it from the overall flux, the energy that goes into the black hole. This is what I did in practice. So this is the variation over the absolute power in gravity waves. And what I find is two different results depending on whether the spins are aligned or anti-aligned. So let me do the aligned case first. When the pulsar is at theta equals 0, so this means the pulsar is on top of the north pole of the black hole. The wave is going in this direction, downwards. The dominant modes are actually the negative M modes and also the negative frequencies. These are superradiant. So most of the incoming energy is in superradiant modes. So overall, the wave is amplified. I have a positive variation of luminosity of the pulsar in gravity waves. In the opposite limit, when the pulsar is at theta equals pi, so the wave is going from here, so from below upwards, I have the positive M and the positive frequency modes being dominant. And this is the case where they are also superradiant, so the superradiant modes dominate. And again, I see a positive variation of the luminosity. Everywhere in between, I have an admixture, which is more or less complicated, of the positive and the negative frequency modes. Let me just go back. This is a reminiscence of this picture that I showed here, that at theta equals 0 and pi, the positive M modes or the negative M modes would be dominant. Okay, and here in the middle I have an admixture of all the different modes. Okay, so this means, going back to the overall picture, so I basically just added all the modes in the incoming part and multiplied each of them by the corresponding gain loss factor that I obtained numerically to get this. So here I have an admixture of both superradiant and non-superradiant modes, and I see the variation compared to the to the flux without a black hole there. It's negative. So I find that basically a modulation of the luminosity depending on the angular position of the pulsar. Because the angular position determines whether the different M modes, which of the different M modes are dominant, and whether the positive or the negative frequency parts are dominant. Okay? If I go to the anti-aligned case, so the black hole is rotating as a spin in this direction, the pulsar in that direction, I can never get amplification. Because here, the positive M modes are dominant, but the negative frequencies are dominant. So these are non-superradiant. And here, I get the negative frequency, the negative M modes, but the positive frequency is dominant. So again, I have an absorption. Mostly, the wave is mostly absorbed by the black hole. So I have a decrease in the luminosity. I also find a modulation, but it's very different from what I find in the aligned case. So if I now put the pulsar, if I think of a binary system, the pulsar is going around the black hole. Let me take an extreme case where I have polar orbits. So I have the pulsar going through the poles in a circular orbit. So this is just a very simple case to analyze. This is the case where it goes through the poles, so the waves I can actually select the positive M modes or the negative M modes. This is where I have a maximal amplification. And I would see this if I could measure the total luminosity of this pulsar and gravity waves. I would see it oscillating like this in the aligned case and oscillating like that in the anti-aligned case. Here, I would see amplification whenever the pulsar is in the North Pole or in the South Pole, North Hemisphere or Southern Hemisphere. Because here is where I can select, essentially, the wave is only superradiant modes here, and here the same thing. Both the positive and negative ends. I know it sounds a bit complicated whether these are positive. I have to see these positive, negative frequencies, but overall the effect is this. I have to check which modes are superradiant, what's the energy they're carrying in the incident wave, and if they're the dominant modes in the incident wave, the overall wave will be amplified. Okay? So I would see a modulation like this, okay? Which is something that in principle could lead to some potential observational signatures. You can see that the effect is this is a kind of an extreme case. This is where the amplification factors are large, and I've taken the distance between the black hole and the pulsar to be around 10 times the wavelength of the radiation. And if I put the pulsar closer, of course I'm going to have a larger effect because the incident energy is large, and the black hole is going to have a larger effect. But I didn't want to go to distances smaller because then I'll go outside my plane of approximation. I have to take other effects into account. I have to take into account the full form of the gravity wave. But even here, I can see that most I can get effects just below the percent level or at the percent level. Something that, in principle, if we're lucky, we could measure in the near future. There's another system that I just want to briefly mention before I finish, which is a compact binary. This is the standard textbook example of something that emits gravity waves, and in principle, this is what we're going to hear about this afternoon. So if you have, in this case, a very simple case, if you have two equal stars with equal masses in a circular orbit, you can't actually see the plane, but this is orbiting in the XY plane, so the equatorial plane of the black hole. It's very easy to compute the moment of inertia of this system. These are just delta functions for each star. This is a standard textbook example. So it's easy to compute the quadrupole moment in the second derivative. And you can actually see that it has up to the overall normalization being different than from the case of the pulsar. I get exactly the same tensor structure, the same easily minus twice omega t. So here, in this configuration when it's rotating the XY plane, I get exactly the same case as I had for the pulsar. Here, for this one. If I tilt the orbital plane, I'm going to get, I haven't done this calculation yet, it's work in progress, but I think I'm going to get the two frequency components as well. But bottom line is, for a binary, if I have a compact binary, it's going to emit gravity waves which are polarized exactly like the ones from the pulsar, because I have the same tensor structure. The H plus and H cross combinations are going to be given by the same spherical harmonics. So the same thing that I showed you just here, if my source instead of a pulsar is a compact binary, so if I have a compact binary, two equal mass stars going around the central black hole, I'm going to see the same effects. But I'm going to see the same effects at a different frequency, because the frequency of the waves depends on the frequency of the orbits of the these compact binaries. So it depends on the orbital period or the orbital distance, because the orbital periods are much larger than the hertz or kilohertz in general. This is going to be in lower frequency regions. Why is this interesting? Because if I think instead of a stellar mass black hole, if I think of a supermassive black holes as the ones that are generically believed to be in the center of active galactic nuclei, with masses that can go from 1 million solar masses in the case of the Milky Way to 10 to the 9 solar masses has been estimated in other active galaxies. The angular velocity of the horizon is now much smaller, in the millihertz range. So if I want to have superradiance around the supermassive black hole, I need something that emits frequencies below the millihertz range. So I need something that has a much longer period than the pulsar, which was just kilohertz or at most hertz. And the binary systems are exactly what I need. So if I want to have 0.1 millihertz in this case, I need a period of the binary which is around 17 hours. It's a short period, but this is something that actually has been observed. For the case of the famous Pulsar-Taylor binary pulsar, this is the one where we have the best indirect evidence for gravity waves. The period was around 8 hours. So I can have these two cases where I have basically the same type of modulation of the luminosity. Either my source is a single pulsar which is rotating and emits gravity waves in the kilohertz region. If this is orbiting a stellar mass black hole, I can find amplification, I can have superradiance. Or if I think about a supermassive black hole that has a compact binary orbiting around it, so like a binary with two pulsars, or even two black holes, okay? Just the period has to be sufficiently small, so it has to be sufficiently compact. I'm going to have superradiance in the millihertz range. This is outside the range of the LIGO and the Virgo and all the ground-based interferometers that are looking for gravity waves in the Earth. But this is the range that LISA, or E-LISA as it's now called, is in principle going to be sensitive. We've been hearing about LISA for, I don't know, ages, since I was way before I was an undergraduate student, I think. So we're not quite sure if this is going to go ahead. I think so. But this is something we could probe in this range. Okay? Just to finish, hopefully I'm still within time. Okay? Well, just to finish, I just want to tell you about observational prospects. What I've shown you is that I have a modulation of the source luminosity as you go around and you have different directions. Okay? I can have effects up to the percent level within the plane wave approximation. But if I make the distance between the source and the black hole smaller, I can have larger effects. So, in principle, this will be more relevant for systems which are close to merging. So, a pulsar or a neutron star that is about to merge with the central black hole, the effect must be larger. I've computed the effect for both electromagnetic and gravity waves. The gravity waves, you need orbital inclinations to be larger than 60 degrees to actually have the dominant modes being superradiant. So you don't actually need the polar orbits, but you need the highly inclined orbits. And the effect is percent level, very close to extremal black holes, but it decreases quite a lot if you go to smaller spin parameters. This means that this is a challenge. This is going to be a very challenging to observe, to get to the level of precision where you can see the gravity waves and you can see a modulation of their luminosity at this level. Of course, we can be lucky. There could be systems in nature that have exactly this property, with black holes very close to extremality, and the frequencies of the pulsars or the compact binaries close to where the amplification factors are maximum. Or we could not be lucky and we have to wait a few years until we reach the required precision. The electromagnetic waves, for example, the magnetic dipole radiation that I mentioned, they're going to be very difficult to detect because, as I was mentioning, this is the very low radio frequencies. Very low radio frequencies are absorbed everywhere. In the case of the pulsar, there's a magnetosphere. It might be absent in some pulsars. There's a plasma there that doesn't allow for very low frequency electromagnetic waves to propagate. There's interstellar medium, intergalactic medium. We can't even observe things from the Earth or even within the vicinity. So I think the case for observing this very low frequency electromagnetic waves, radio waves, is very difficult. The gravity waves, on the other hand, they don't interact with anything. Okay, so they're not absorbed by the astrophysical plasmas. They would reach this intact. That's why they're so difficult to detect. But I think this is why one of the reasons for me that what we're expecting from today's announcement is that they actually found gravity waves, and if they manage, this will open up a whole new field in astrophysics and observational astronomy using gravity waves. And this is one of the things that I think can be used. I'm trying to go beyond all my approximations. I've just done very particular spin alignments. I'm going beyond this, different orbits, going beyond the plane wave approximation, and including effects not of the total luminosity, but something that you see, things that you see along a particular line of sight, where the results are not going to be exactly as I showed, but qualitatively will be very similar. Okay? Just let me give you a summary. I hope this was not too technical, but the main ideas that I want you to take from this talk are that we can have an amplification of plane waves by a rotating Kerr black hole. The waves have a sufficiently low frequency. If there's a directional dependence, I'm going to see this modulation. But I need the polarization of the waves to be able to have the superradiant modes dominating over the non-superradiant modes. This is the basic idea. And there are systems like Pulsar-black binaries, compact binaries around the central supermassive black holes or triple system, where these requirements are all met. So superradiance can really occur in astrophysical systems. There might be observational signatures, so things that we can see with the square kilometer array planned with advanced LIGO, which I underlined because, well, today it might be the day that they say something. And advanced Virgo, there's Cagra, there's lots of gravity wave observatories coming online in the near future. And this can be a very good test of general relativity in the near future, something they can use to actually test this very unusual property of the Kerr geometry, which is to amplify waves that are incident in this geometry. So thank you very much for your time. Yeah? You mean in the toy model? That Schrödinger problem, is it? Yes. No. Actually, no. So here in this toy model, I just put an alpha, generic parameter which determines the height of the barrier. Okay. So the height of the barrier actually depends on the frequency, so I didn't include this in the toy model. This was just to illustrate how that the reflection coefficient can be larger than 1 in this range of frequencies. If I showed you I can show you, for example, here, the gain loss factor. Okay? Besides being proportional to that combination, it goes like omega to the L2L plus 1. In the case of gravity waves, the minimum L is 2. The L cannot be less than C. So here's 2 times 2 is 4 times 5. So if you go to smaller frequencies, this decreases. Okay? And actually, if I showed you here, you go to lower frequencies, the amplification, the gain loss factor goes very small. And this is actually true both for the positive case and for the negative case. Okay? So very low frequency waves are not very much absorbed, neither absorbed nor amplified by the black hole. If the wavelength is very large, it basically doesn't feel the black hole is there. It's kind of, I think that's kind of the intuitive way. Okay? The peak, so the amplification occurs, the maximal amplification occurs for this node, L equals M equals 2. Okay? When the frequency is very close to being twice the angular velocity of the horizon. It seems like fine-tuned. If you go below, the amplification factors go small. This is why I told you that as soon as if you go to frequencies which are not exactly quite there, the effect becomes much, much harder to detect. Okay? So we would need, but this basically just quantifies the precision that we would need to measure the luminosity of a particular source to see that modulation. Of course, in principle, if you have an arbitrary precision, you would be able to observe this in any system. But we haven't even detected the gravity wave, so we have to wait to reach at least I think at the percent level, we can hope that there is some system where the frequencies are actually matching in that region. At least the numbers within the kilohertz for stellar mass black holes, within the millihertz, it's very possible, okay, that this happens. Whether nature gives us a present and we can test this really in nature, we'll have to make this. No. This is like, yes, and this is people have thought about this. It's not exactly the same as the Klein paradox. It's related to that, but there's actually no paradox here. It's not the same interpretation. The interpretation is that these waves. Let me go back here. So you see that close to the horizon, so this is region 1, the phase velocity, if you go to omega less than m, omega changes sign. But the group velocity doesn't. So this means that the waves are actually going into the horizon, but they have a negative phase velocity. It's like they're carrying a negative energy into the horizon. This is from the point of view, carrying a negative energy at the horizon, from the point of view of an observer at infinity. So it means that the observer at infinity, if it's going to measure it sees the wave coming out of with a larger energy and the black hole losing its energy, its mass and spin. So this is something that you can actually, there was only recently a paper that did a full numerical analysis in general relativity to show, so not just perturbing the Einstein equations on top of a fixed background, but allowing the background to vary as well, to be back reacted by this wave. So you can actually, in that case, you can actually see the waves coming out with a larger energy, very similar to the test field approach, and you can see the black hole losing its mass and spin because of the process. Okay, so it is the interpretation of this phenomenon. It's kind of hard to explain. For me, this is the easy way to understand is that this in general relativity you're allowed to have negative energies. The concept of energies is observer. An observer at infinity can measure a wave going into the horizon with a negative energy. And the interpretation of this is that the black hole is losing energy. This is something that has been shown using full numerical simulation. Okay? The full numerical simulation is because it's very difficult to treat Einstein's equations. They are nonlinear. Okay? But the full nonlinear problem, where you have not just a wave on a fixed spacetime, but allow both the wave and the spacetime to evolve. I hope I've answered your question. Yes. Superradiance occurs in high dimensional black holes. I mean, the superradiant condition is the same. Okay? Of course, if you have Myers-Berry, you have two spins, and so you have to. It's just like a singly spinning one. It can become a bit more complicated to analyze. I'm not sure if there's been analysis of actually computing how different these reflection coefficients are in high-dimensional black holes. I know one thing that I've studied. I didn't mention this, which are superradiant instabilities, which are related to this. Maybe you've heard about this. Superradiant instabilities occurs when instead of a massless wave, you have a mass, for example, or if you would put a mirror around the black hole. This was an idea back in the 70s. This toy model would be to put an infinite potential there, so you would get bound states. And you see that these bound states in the superradiant regime, they get an imaginary parts, which is positive. It means that the bound states have an amplitude which is actually growing. So the result of superradiance is that if you have some waves that can be confined there, they are continuously being scattered and amplified, and you get an instability. Okay? So what people have shown is that in higher dimensions, you always have superradiant scattering, but the superradiant instabilities are not always present. Not always present. Only black strings and black grains in particular. If you want, I can explain to you the technical reasons afterwards. But superradiant scattering exists in high-dimensional black holes. Okay, thanks a lot.